Now, let us classify crystalline solids. Crystalline solids can be classified into four different categories depending upon the type of constituent particles and the nature of attractive forces operating between them. They are: first one, molecular solids; second one, ionic solids; third one, covalent or network solids; and the last one, metallic solids. Firstly, let us take up molecular solids. In molecular solids, the constituent particles are molecules. Depending upon the nature of molecules, these solids are further classified into three types: nonpolar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. What are nonpolar molecular solids? In nonpolar molecular solids, the constituent particles are either atoms like noble gases such as helium, neon, argon, etc., or nonpolar molecules like H2, Cl2, I2, CH4, etc. Generally, they are liquids or gases at room temperature and they exist as solids at supercooled temperature. In these solids, the electron cloud is symmetrically distributed and the molecules does not have any polarity. Sometimes these atoms and nonpolar molecules lose their symmetry in electron cloud distribution for a shorter time and produce instantaneous dipole. These dipoles distort the electron cloud of the neighboring atom or nonpolar molecule, including dipole moment in them. Now, electrostatic force of attraction between these instantaneous dipoles are called as dispersion forces or London forces. Due to the presence of weak forces, these solids have low melting point and boiling point. Let us study about polar molecular solids. In polar molecular solids, the constituent particles are polar molecules like HCl, SO2, etc. The molecules of these solids are held together by dipole-dipole forces of attraction. Due to the presence of dipole-dipole interactions, these solids are soft and their melting and boiling points are comparatively higher than those of nonpolar solids. But still, as these solids do not have very high melting and boiling points, they exist as gases or liquids at room temperature under ordinary pressure. Now, let us study about hydrogen bonded molecular solids. In hydrogen bonded molecular solids, the constituent particles are molecules which contain hydrogen atom linked to highly electronegative atom such as fluorine, oxygen, or nitrogen of neighboring molecule. This link between hydrogen atom and highly electronegative atom of its neighboring molecule is known as hydrogen bond, and the hydrogen bond is represented as dotted lines. Due to the presence of strong hydrogen bonds, these solids have higher boiling and melting point when compared to nonpolar and polar solids. These solids are poor conductor of electricity and they exist as volatile liquids or soft solids at room temperature and pressure. Let us consider metallic solids. In metallic solids, the constituent particles are metal ions and free electrons. Metals have a tendency to lose electrons and becomes positively charged ions. These group of positively charged metal ions are called as kernels, and the electrons can easily flow throughout the metal crystal like water in the sea. These mobile electrons are attracted by the positively charged ions and holds these ions together. The attractive force that holds the kernels and the mobile electrons in the metallic solid is called as metallic bond. Due to the presence of strong metallic bonds, the metallic solids have high melting points and boiling points. The free electrons in these solids are responsible for high electrical and thermal conductivities of metals. In fact, the color of certain metals are also due to the presence of these free electrons. Some of the examples of metallic solids are copper, iron, aluminium, silver, etc. Let us discuss about ionic solids. In ionic solids, ions are the constituent particles. In these solids, there is a three-dimensional arrangement of cations and anions that are held together by strong electrostatic force of attraction. As a result, these ions are not free to move and are closely packed, and hence these are hard and brittle solids. Ionic solids possess high melting and boiling points. Being ionic in nature, these solids are soluble in polar solvents like water, but insoluble in nonpolar solvents like ether. Ionic solids act as insulators in solid state, but in aqueous solutions or in molten state, they act as a very good conductor of electricity. Here, the question is, why are ionic solids very good conductors in the molten state and not in the solid state? In ionic solids, the electrical conductivity is due to the movement of the ions. However, in the solid state, the ions are in fixed positions and they are not free to move. However, in molten state or aqueous solutions, the individual ions are free to move. And when potential difference is applied, these ions act as a charge carriers and become good conductors of electricity. Some of the examples of ionic solids are sodium chloride, zinc sulfide, magnesium oxide, cesium chloride, etc. Now, let us discuss about covalent solids. These are crystalline solids in which the constituent particles are non-metal atoms linked to adjacent atoms by covalent bonds throughout the crystal structure. As a result, network of covalent bonds are formed. Due to large network of covalent bonds, these solids are also known as network solids. These solids are very hard and brittle and have extremely high melting and boiling points. These covalent solids, due to the absence of free ions, act as bad conductor of electricity. One of the most common examples of covalent or network solid is diamond, where each carbon atoms are linked together by 4 covalent bonds to give a three-dimensional structure. However, there is one exception whose properties are quite different from the other covalent solids. Let us study about that exception. And the exception is graphite. Though it is a covalent solid, unlike other covalent solids, it is soft and good conductor of electricity. This exceptional behavior of graphite is due to its typical layer structure. In graphite, carbon atoms are arranged in different layers. We know that carbon is tetravalent in nature and has 4 valence electrons. In each layer, one carbon atom is bonded to 3 other neighboring atoms within the same layer. The unbounded 4th valence electron of each carbon atom remains unbounded and is present between the layers. This fourth valence electron is free to move within the structure. When potential difference is applied, these free electrons act as a charge carriers and makes graphite a good conductor of electricity. The force of attraction between each layer of graphite is very weak. Due to this, different layers can easily slide over the one another. This makes graphite soft and good solid lubricant. Best examples of covalent solids are diamond, silicon carbide, silica, etc. Crystal lattices and unit cells. Consider a crystal. We know that the main characteristic of crystalline solids is its regular and repeating pattern of constituent particles. Now, when we replace these particles with representative points, a crystal lattice is obtained. Crystal lattice is defined as the three-dimensional arrangement of constituent particles represented diametrically such that each particle is depicted as a point. Such an arrangement is known as crystal lattice. There are 14 possible three-dimensional lattices known to us. These lattices are named after the French mathematician who first discovered it. Thus, they are known as Bravais lattices. Now we know what is crystal lattice. Let us study some of its characteristics. Now we know what is crystal lattice. Let us study some of its characteristics. First one, each point in a crystal lattice is called lattice point or lattice site. Second one, each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule, or an ion. Now, if we observe this crystal lattice, we can notice that there is a small group of lattice points that repeats itself again and again to form an entire crystal lattice. This small group of lattice points is known as unit cell. Therefore, unit cell is the smallest portion of a crystal lattice. When repeated in different directions, generates the entire lattice. A unit cell is represented by three edges A, B, and C represented along X, Y, and Z axis. Please note that all these edges may or may not be mutually perpendicular to each other. In some cases, they are mutually perpendicular to each other, and in some cases, they are inclined to one another. In this unit cell, the angle between the edges B and C is alpha. The angle between edges A and C is beta, and the angle between edges A and B is gamma. Overall, a unit cell is characterized by 6 parameters, that is A, B, C, which are edge lengths, and alpha, beta, and gamma, which are phase angles. There are 7 possible combinations of A, B, C, and alpha, beta, and gamma, forming 7 types of unit cells. These are also called crystal systems. They are cubic unit cell, tetragonal unit cell, orthorhombic unit cell, hexagonal unit cell, rhombohedral or trigonal unit cell, monoclinic unit cell, and triclinic unit cell. Let us tabulate all these characteristics in a form of a table. Dear students, please memorize these characteristic properties as they appear in competitive examinations.
Calculations of number of particles in a unit cell. A crystal lattice is made up of a very large number of unit cells. Each unit cell is touching a number of other unit cells. In a unit cell, every lattice point is occupied by one constituent particle. Thus, a constituent particle present at the lattice point may be shared by a number of unit cells. Let us now understand the contribution of a particle in a lattice point to its unit cell. A corner atom is shared equally by 8 unit cells. 4 unit cells are present in the lower layer and 4 unit cells are present on the upper layer. Therefore, each corner atom contributes only 1/8 atom to a particular unit cell. A face-centered atom is shared equally by 2 unit cells, having a common face. Therefore, an atom present at the center of the face of a unit cell contributes half atom to each unit cell. A body-centered atom is not shared by any adjacent unit cell in a crystal lattice. Therefore, it contributes fully to a unit cell. A edge-centered atom is shared by 4 adjacent unit cells in the crystal lattice. 2 unit cells are present in the lower layer and 2 unit cells are present on the upper layer. Therefore, it contributes only 1/4 of itself to a unit cell. Calculation of number of atoms per unit cells in primitive cubic unit cell. Simple cube. In simple cubic unit cell, there are 8 corners in a cube. There is 1 atom at each corner of the cube. Since each corner atom is shared equally by 8 unit cells, hence, each corner atom contributes 1/8 atom to each unit cell. Number of atoms in one simple cubic unit cell is equal to 8 into 1 by 8, which is equal to 1 atom. A simple cubic unit cell contains 1 atom. Calculation of number of atoms per unit cells in body-centered cubic unit cell. In a body-centered unit cell, there are 8 atoms at each corner positions and 1 atom at its body center. As each atom at the corner position contributes 1/8 to the unit cell, the contribution of those 8 corner atoms to the unit cell is 1 atom. The atom at the center of the unit cell is not shared by any other unit cell. Thus, its contribution to its unit cell is whole. Hence, the number of atoms per body-centered unit cell is 1 plus 1, which is equal to 2. 8 corner atoms into 1 by 8 is equal to 1 atom. 1 body-centered atom is equal to 1 into 1, which is equal to 1 atom. Therefore, number of atoms per unit cell is equal to 2 atoms. Thus, a body-centered cubic unit cell contains 2 atoms of an element. Calculation of number of atoms per unit cells in face-centered cubic unit cell. In a face-centered cubic unit cell, there are 8 atoms at the corner positions and 1 atom at the center of every face of the cube. As each atom at the corner position contributes 1/8 to the unit cell, the contribution of these 8 corner atoms to the unit cell is 1 atom. Each atom at the face center is shared between 2 adjacent unit cells. Thus, the contribution of 6 such face-centered atoms to the unit cell is 6 into 1/2, which is equal to 3. Therefore, the total number of atoms per face-centered unit cells is 1 plus 3, which is equal to 4. 8 corner atoms into 1/8 is equal to 1 atom. 6 face-centered atoms into 1/2 atom per unit cell equal to 6 into 1/2, which is equal to 3 atoms. Therefore, total number of atoms per unit cell is equal to 4 atoms. The face-centered cubic unit cell contains 4 atoms of an element.